All right, so let's talk about relations and functions. To understand relations and functions, we need to get two things out of the way, an input and an output. It's new vocabulary for things we already know. And so for instance, the x-coordinate if you recall, the x-coordinate is the coordinate that we used to plug into an equation when you wanted to find your y value. So for that reason, this is called our input. The x-coordinate will become our input value, and our y-coordinate, and again, if you recall, the y-coordinate was the number or the calculated answer we got after you plugged in an x-coordinate or an x value into any equation. So we call that one the output or output value. So that's just new vocabulary for things we already know, and it's mainly just telling us what we did with those coordinates. So instead of just saying the x-coordinate, we now know that that's the input, and instead of just calling it the y-coordinate, that's going to be our output. So when students ask me, which is the number that we can pick when we're doing a table, I always told them it's the x-coordinate that you get to pick. Why? Because that's the one you're going to be plugging in. And you have no control over what the output is. It's the equation that gives you the output. So now let's get to a relation. What is a relation? Kind of sounds like relationship, and that's kind of what it is, right? It's what's happening with this number and how is it related to this number. So let's write down relation. And a relation is when an input pairs with an output. Right? So we've seen coordinate lists before, and they are now represented a little different when you talk about relations. Input pairs with an output. So when an input pairs with an output, that looks like a coordinate point, right? An ordered pair. So what we used to call ordered pairs, x and y coordinates, we're going to just call them input-output. And that's going to be written in a mapping diagram. So it's going to look a little different, but I'm going to show you the similarity between them. So first, let's just talk about some ordered pairs. So ordered pairs such as 0, 1. That is an input pairing with an output. Another ordered pair, 1, 2. Another one, 2, 4. So this is a list of inputs, or x-coordinates, pairing with an output, our y-coordinates. Now this was our old terminology, but now we're going to do something called the mapping diagram. And the term mapping is kind of like something linking to something else or something going onto something else. So it's like a direct relation between two things. So in a mapping diagram, you've got two bubbles. And in the first one, you have all your inputs. And in the second one, you have all your outputs. All right, so if you want to write that down, these are your inputs. These are your outputs. And the way a mapping diagram works is it's showing you that when you have 0 as an input, the output was 1. When 1 was the input, the output was 2. And when 2 was the input, the output was 4. So in a mapping diagram, you follow the arrows that shows you what pairs with what. All right, so let's practice understanding how these work in the mapping diagram. So example 1. List the ordered pairs. All right, so here's a mapping diagram. We'll have two examples. Say you had 1, 2, 3, and 4. Then you had 3, 6, 9, and 12. And 3 was mapped to, 1 mapped to 3, 2 was mapped to 9, 3 was mapped to 6, and 4 was mapped to 12. And then for B, all right, so in a mapping diagram, they're in order from smallest to greatest. And you're going to show you, I'm going to show you that 2 goes to 1, 0 goes to 0, 2 also goes to -2, and 4 goes to -3. So, what are the coordinates in these mapping diagrams? So, solution. The ordered pairs would mean input of 1 corresponded to output of 3. The next one, 2 corresponds to 9 or is paired with 9. And then you also have 3, follow the arrow, being paired with 6, and 4 being paired with 12. So those are your input-output pairs, which become your coordinates or ordered pairs. Same thing with this one. Follow the first one. 0 is input, makes a 0 output. 2 as an input is paired with 1 as an output, and so forth. 2 also goes to -2, so every arrow gets followed to create a new coordinate. And 4 gets paired with -3. All right, so that's how you go from a mapping diagram to some ordered pairs. And one thing we need to acknowledge is what a function is. So let's write the definition of a function. In pairing these ordered pairs, there's something that we have to look out for, and that is to find out if a relation is a function, that means every input only has one output. It's a relation that pairs and each input with exactly and that's very important, one output. All right, so it has to have one output. If you're plugging something in, there should only one thing that comes out as an output. Okay, so let's look at example 2. And you're going to tell me if it's a function. So here's a scenario, example 2a. Say you have -9, -2, 5, and 12. And it's being mapped to these numbers over here, 0, 5, and 10. So if I'm telling you that -9 goes to 0, -2 maps to 5, 5 maps to 10, and 12 maps to 10. And for B, -2, -1, 0, 1, 2. And then you have 3, 4, 5, 6, and 7. And they're linked as such. Okay. The question is the relation a function? So looking at our definition, we can only have one input, which are these, and you just follow the arrows. You can tell that if these are the inputs, the outputs are where the arrow is ending or going towards or pointing to. All right, so we check our inputs. -9 only has one output. -2 only has one output. 5 only has one output and it's 10. 12 only has one output and it's 10. So does each input have exactly one output? The answer is yes, it does. So we call it a function. All right. Now the next one. Does each input have exactly one output? -2 is only paired with 4. This input, -1, only has 3. This 0 is paired with 5, and this 0 is also paired with 6. 1 is paired with 6, 2 is paired with 7. So are any of these inputs have more than one output? And the answer is yes. 0. 0 has 2 outputs. That's not allowed. Every input should only have one output. So for this one, we're going to say no, not a function. All right. So I have an analogy that'll help students apply this exactly one output rule to something more relatable, and that is in relationships. So in a relationship, you're not supposed to be with 2 people at the same time. So if you're thinking of seeking 2 people simultaneously, then you're considered cheater, and the relationship's not going to work. So we're going to look to see if any of these values are seeking 2 people at the same time. -9, all good. -2 is all good. 5 is going after the 10, and 12 is going after the 10. 5 is doing nothing wrong, 12 is doing nothing wrong, but what's happening here is that 10 is attracting 2 numbers. The 10 is not guilty of anything, it's nothing wrong, because it's only attracting 2 numbers. So if 2 people are interested in you, does not make you guilty of anything. However, if you're the one interested in 2 people at the same time and you're pursuing that, then that's a problem. So that's what's happening over here. And in my analogy, you have 0 seeking the 5 and that 0 seeking the 6. So this is the problem right here. Over here, it looks like 6 is attracting the 0 and the 6 is also attracting the 1, but the 6 is not guilty of anything. So the story that I like to think about is, think about the guiltiness. Is there a number that is seeking 2 other values? And they got to be different values. And then that would be a problem. So that's how you can tell if it is or is not a function. All right, so I'm just going to show you a couple more. And this is just for practice, so you don't have to write these down, just to kind of discuss and see if we got the hang of this. So here's 4 more. They're not written in mapping diagrams, but we do just want to identify which ones are our inputs, which ones are our outputs. So putting that little story analogy into play, let's see what's going on here. So say you have your inputs on C would be 4, 0, and 2. These are the ones that are seeking a partner. 4 is seeking 3, nowhere else. 0 is seeking the 3, 0 doesn't appear to be seeking another one. And 2 is seeking the 4, and it doesn't appear to be seeking any other one. So 4, 0, and 2 It's all good. None of them are doing anything wrong, so we'll say yes, this is a function. D, just watch and think about this. Is there a problem with these input values here? Here I have a -1 seeking 9 and a -1 seeking the 4. And it is an input because they're listed under the x coordinate. So this is the problem. So we're going to say no. It's not allowed to have two partners. E, we have 3, 4, and 3. Notice I'm only underlining the inputs. Reason for that is it's the inputs that are seeking the other numbers. The outputs are y coordinates. Those are the ones that are just attracting numbers, but they're not doing anything wrong. They're probably not even interested in pursuing anything. So 3, look what we have here. 3 is seeking the 7, and that same 3 over here is seeking -6. That's a problem. So we say no, it's not a function. For F, here are my inputs. I'm checking to see if -3 anywhere else is with another number. Nope. 2, anywhere else is the 2 with another number? No. 1, is there another 1 anywhere else with another number? No. And 0, doesn't appear to be anywhere else with another number. So only focused on my inputs, each one only has one partner or is seeking only one number, so it's all good. We say yes, it is a function. All right. Now you might argue here that you see that this is -5s. This -5 is an output value. It's attracting a -3, and the -5 is attracting a 1. The -5 is not seeking, right? The -1 is just attracting two numbers, but the -5 doesn't do anything wrong. It's just attracting. So it's not the one that's out there seeking, doing it intentional. So there you go. That's my little analogy that helps me help students understand this whole one-to-one input-output corresponding.